Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss about the frictional loss in a pipe flow. So, for discussing this frictional loss in the pipe flow, let's draw first a pipe and through which we can show the liquid which is flowing through that. And let's draw the diagram of this pipe in this way. We can draw. And let's draw the center line of the pipe. Yeah. Now, the liquid which is flowing with a velocity of u, suppose capital U or capital V we can consider for this. Now we know that when the liquid is flowing through a pipe, the velocity of the liquid layer adjacent to the pipe wall, you can say this is the pipe wall. Okay, at this level the velocity of this liquid is considered as 0. Okay, is considered as 0, and the velocity of this liquid is continuously increasing up like this. Is continuously increasing like this. Again from here if you take, again it will be like an increasing mode will be there. So the velocity gradient for this is the velocity gradient actually, you can say. Let me show you here. If you see, this is the velocity for this region. Next region, this is the velocity. Next region, again some velocity increasing. So the difference between these two layers, okay, so that is called here velocity gradient, which already we have discussed during our Newton's law of viscosity. Okay, so this velocity increment or the velocity is 0 at this point. This is due to the viscosity of the liquid. Okay, and the loss, we can say this viscous effect or the viscous action, we can say. Okay, this causes the loss of energy. Due to this, the loss of energy, we can say. Why? Because the loss of energy we are talking, because when the velocity of fluid is, suppose considered here, it is 10 meter per second, and when it is entering to this pipe, everywhere the same velocity is not there. Okay, here it is 0, here it is 1, 2, 3, like that we can get it. So there is a decrement of velocity in the liquid when it is entering into the pipe flow. That's why it is called the loss of energy. And this loss of energy due to the viscosity is happening, so that this is known as the frictional loss. This is called a frictional loss in the pipe flow. Okay, now on the basis of this, okay, William Froude, one scientist, okay, he did one experiment. William Froude did one experiment, and he found something for a turbulent flow. This is when it is a laminar flow. Actually, when the fluid is flowing with laminar flow, or the velocity is very less, that much effect will be not there. Okay, or that means losses will be also not there. But when it is coming to the turbulent flow, when we'll see the liquid is flowing with a turbulent flow, that means high velocity. At that point, few points need to be considered, or we can say the frictional losses which is happening. For that we need to consider. So he given some concept of frictional resistance. Okay, the frictional resistance for the turbulent flow. So the frictional resistance for the turbulent flow is given is it is directly proportional. It is directly proportional to the velocity of the liquid. Actually, in the last class also we have discussed these things. Okay, for a turbulent flow, in the Reynolds experiment we have discussed this one. So this frictional resistance is directly proportional to the V to the power n. Actually, this n is nothing but this is vary from 1.2, 1.5 to 2. So we can write this is directly proportional to V square also. Now this frictional resistance also for the turbulent flow is also proportional to the density of the fluid. What is the density of the fluid? Next, this is also proportional to the area of what is the surface of contact. That means the liquid which is passing through this pipe, what is the area of contact, that also a region is there. And also along with that, pressure is there, but this is independent of pressure. There is not directly proportional to the pressure, so it is independent of pressure is there. So these are the points was given by the William Ford for this frictional resistance. Okay, now for this we are going to derive an equation. What is the equation, or you can say expression? We are going to derive expression for loss of head, or you can say the loss of energy. Okay, the loss of energy or loss of head due to what? Due to the frictional in the friction in the pipe. So you can write expression for loss of head due to friction in pipe. Friction in pipe. So now we'll derive an equation for this. Okay, for this derivation, actually we need the help of Bernoulli's equation. Okay, so we already studied the Bernoulli's equation. So if you remember the Bernoulli's equation, now for applying the Bernoulli's equation, we need to consider two sections in this pipe. This is one section, this is another one section. So mark it as a section 1, okay, and mark it as a section 2. Okay, what is the section 1 and section 2? Now when the liquid or fluid is flowing through the pipe, okay, it covers, or it is travels certain distance. So what distance it is covering, or what distance it is flowing, though it is flowing from here and is leaving it out from this point, inlet and outlet point, but in this region we will just consider two different sections, and through which we can consider the Bernoulli's equation, section 1 and section 2. So this is a length of L, and this diameter D is there, and next, yeah. So when we are talking about this concept, now again we need to see what is the pressure impact, what is the intensity of pressure at the section 1. So when the fluid is flowing in this region, so there is a pressure intensity will be there at this flow. Similarly, this is suppose P1, because it is section 1, let P1 be. Now similarly at the section 2, again we have a pressure intensity will be there, which is opposite to the fluid flow. So that is pressure P2 at the section 2. Okay, this is P1, that is a pressure intensity at the section 1, and here this is P2, which is pressure intensity of section 2, and which is reversed to the fluid flow. Okay, now at this point also we need to consider the velocity V1. Okay, what is the velocity at this point particular? Similarly here also we can consider velocity V2. Okay, now when the fluid is flowing, as I told, so there will be some opposite force which is impacting here due to the friction here. So this is also a frictional force which is going to, we can just only mark here F, or F1 also we can mark it here, there is no issue on that. Okay, now to derive this expression we need to consider a few things are there, as I told. Okay, what is that? The P1 is the pressure intensity at the section 1, V1 is the velocity at the section 1, and similarly P2 pressure intensity at the section 2, and this is P2, we can consider that is the velocity, the liquid velocity or fluid velocity at the section 2. Along with that we need to consider few other points are there. That means some other terminologies are there, like as I told, length of the pipe, what is the length of the pipe or the diameter of the pipe, so that also need to be considered. So let's write here length of the pipe between the section 1 and 2, not the total pipe length, only in between the section 1 and section 2. Similarly diameter of the pipe. Now next is we can consider F dash. This is a new terminology, F dash. This is F dash is nothing but this is a frictional resistance per unit weighted area per velocity, per unit velocity. This is frictional resistance per unit weighted area per unit velocity, that is F dash. Similarly, we need to consider the HF. HF is nothing but the head loss due to the friction. What is the, as I told you here, the loss of energy or the loss of head. This is happening why? Because this is due to the friction. This is happening due to the friction. So that also we need to consider HF. So these are the terminology we need to consider to derive this. Now we can apply the Bernoulli's equation. So we know that the Bernoulli's equation, let's write the equation of this: P1 by rho g plus V1 square by 2g plus Z1 equal to P2 by rho g, and this is V2 square by 2g plus Z2. And along with that, we need to include the head loss, because there is a fluid is flowing and that to be real fluid. So there will be a head loss will be there. That's why we have written HF here. So HF need to be written in the section 2 side. Okay, when it is traveling through a distance, then only we can get the loss of head. Now, if you see the equation here, Z1 and Z2, these two are same, because Z1 and Z2 is nothing but is the height of this fluid or height of the pipe through which the fluid is flowing, at what head it is situated, at what height it is situated. So if you see a section 1 and section 2, both this pipe is a horizontal case. So we can consider Z1 equal to Z2. Okay. Now this is okay. Now similarly, V1 also we can consider V1 equal to V2, because the diameter of this pipe is same. The diameter of the pipe is same for both the sections. So that we can consider V1 equal to V2. Why? Now we know that Q equal to continuity equation A1 V1 equal to A2 and A2 V2. So that what is the diameter is there, same diameter will be also here. So that's why we can write A1 V1 equal to A2 V2. Now by applying this one, finally what we are going to get, see, this is gone, this is also gone, this part also gone, this part also gone, because these all are constant value. So we can write equal value. So we can write now HF equal to P1 by rho g minus P2 by rho g, and give this equation 2, and this equation we can mark it equation 1. So I hope you understood till now. Now what I'll do, HF, as I told you, this is the head loss due to the friction, so that the intensity of pressure can be reduced in the direction of flow by the frictional resistance. Now we can write the frictional resistance. Let's see the frictional resistance equal to, I can write the frictional resistance per unit weighted area per unit velocity, that is F dash, into the weighted area. The weighted area, that is nothing but pi dl. This is the weighted area, that how much area was covered by that, or it is flowing through the liquid. So frictional resistance we can write F dash into weighted area per unit velocity. So per unit velocity, so that is V square. Already we have seen the directly proportional frictional resistance directly proportional to the V square. So these are the points need to be multiplied here. This is the weighted area pi dl, and the velocity, as I told, V1, V2 all are same. So we can write V1, V square. So now this one we can write F dash into P, I can write this one, pi d, I can write the perimeter, P into L into V square. Okay. So this is about the frictional resistance. Now let's find out between the section 1 and section 2, what are the forces are impacting on that, or what the forces are acting on this between this section 1 and section 2. So this is about the frictional resistance what we got. Now let's find out what is the forces are acting between section 1 and section 2. Forces are acting between 1 and 2. So first one, I can write the pressure force at section 1. So that is nothing but we can write simple P1 into A. Now you can ask how it is pressure force equal to P1 into A. Now we know that very simple, pressure equal to force by area. Now if I want to write force, so I can write pressure into area. So this is the same thing here. What is the pressure force? Is the force equal to P1 into A. So here A is the area of the pipe. Now similarly, pressure force at section, this is, let's write section 1, and this is PF at section 2. This also we can write, let 1 to leave it. Okay, now this is P2 into A, similar. Now again, one more thing is the third one, another one force I have given there, that is frictional force I have given in the diagram. If you see this one, F1, okay, we can mark only F or F1 or F2, something we can give it here, no issue, symbolize. So this is the frictional force also. Now these are the three forces. Let's resolve it. Let's resolve these are the forces in horizontal direction, in the which direction the fluid is flowing. So for resolving, we know that we can write summation of force equal to 0. Okay, so summation of force equal to 0 is nothing but, what are the forces are there? Let's write P1A in the forward direction minus P2A in the reverse direction minus F1, this is also in the reverse direction, that is equal to 0. So now we can write what? Now we can write this PA, we can take common here. So let F1 take it to other side. So what I'll do here, P1 minus P2 bracket A equal to F1. So this F1 is nothing but, as I told here, frictional force is there. So so this one we can write, this is nothing but the frictional resistance. So this also you can write F dash into P into L, this value I can write into V square. Okay, now what I'll do, I'll just write this P1 minus P2 is equal to this divided by, we can write F dash P L V square divided by A. Okay, now so in the previous equation, if you see, we have already got previously here. If you see here, this one, up to here only I have written. Next point also we can write here. That means P1 minus P2 equal to HF rho G. Here we can write, one more term we can write, P1 minus P2 equal to rho G H. So H here, HF is there. So this one we know that P, we know the equation P equal to rho GH. So here also with the pressure difference we got rho GF. Yeah. Now just put the value of rho GF here. So we can write rho GHF equal to, this is the value, F dash P L V square by A. Okay. Now what I'll do, I'll just keep only HF one side. HF let keep one side, and this rho G take it to another side. So we can write F dash P L V square divided by rho G A. Okay, rho G A. Now if you see this value P by A in this equation, P by A is nothing but P equal to what? Now P equal to perimeter, weighted perimeter. Okay, and A is the area. So let's write P by A equal to, I can write, this is pi d and this is pi by 4 d square, correct? This is the perimeter, weighted perimeter, and this is the area. So this formula is pi d and this formula is pi by 4 d square. If you solve this, we'll get 4 by d, because pi will be cancelled and this will be cancelled, d will be there, and 4 will go to the numerator. So P by A equal to 4 by D. So this, put this value here so that we can get, what we'll get here, again just I'll write here, put the value here in this equation. So I can write F dash by rho G 4 by D LV square. Okay, F dash by rho G, yeah, LV square, correct. Now what is our intention? Now we need to find out final, what is the head loss value. So HF equal to, I can write here, now 4 here, I can write here. Now next, one more thing, this F dash by P, or you can say the F dash by rho equal to, you can write let me give me a bracket here. So here what I got, f dash by p equal to, let write f by 2. Why? Because I'm taking this one, because here the coefficient of friction, we need to convert this term, this one. So I can write this f dash by p equal to f by 2, and this f is nothing but coefficient of friction. Now f dash by p where? Now here it is there. Now again we need to do, well, the p term is there. Yeah, p by area already we have, this one already we have changed this one, correct. Now p f dash by, this is rho actually, not p, this part actually we need to change it. Okay, now finally what we'll get, now hf equal to, we can write 4f lb square divided by, how much is there, 2g d. Okay, now this is the equation what we are going to get. Okay, this is the only things we need to do in the last, f dash by rho we need to convert into f by 2, and finally we are going to get, this is the equation. So in this equation you see hf is nothing but the head loss, as I told, 4f lb square by 2g d. So the f is nothing but the coefficient of friction. Okay, and L is the length, B is the velocity, D is the diameter of the pipe, and this equation actually called Darcy-Weber's equation. Darcy-Weber's equation. Okay, and this equation also we used to call the frictional loss. This is the major loss equation also, which we are going to study in the further lecture. Okay, so there also I can skip that and I can show this video that this we already have derived this equation, Darcy-Weber's equation, and this is due to the frictional loss, and this frictional loss is considered in the major losses in the pipe flow. So I think this is enough. Okay, and here finally we can close it here, or else if you want to solve many in that equation, then also we can sort it down also. Okay, so that also can be written. Now I hope you understand this equation. If you are having any kind of query regarding this, you can give a comment on the comment box. So let me highlight a few points. These are the things we have discussed due to the frictional resistance for the turbulent flow, and this is the diagram of this concept, and after that directly you go for the expression. From the expression we need to consider this Bernoulli's equation. Okay, you need to remember the Bernoulli's equation, where pressure energy, kinetic energy and potential energy, three energy equal at this point plus at this point. These are pressure energy, kinetic energy, or this is the potential energy, you can say. So both at this section 1 and section 2, and due to the losses between these two sections, HF. Just you put this value of Z1 equal to Z2, B1 equal to B2, because due to the same head or same height is content, plus velocity is constant, or velocity is same, because diameter is same. That's why velocity can be considered the same, because due to this continuity equation here. Okay, yeah, now we can go for the next part of this, frictional resistance. So frictional resistance, as I told you already when I told this F dash point, this one. Okay, there I told this is the frictional resistance is nothing but what the friction of the per unit weighted area per unit velocity. So this is the equation for this. Now from here what we got, you can keep it there. Now go for the forces. What are the forces are acting in the section 1 and section 2? As I told, this is P1 and P2 intensity of pressure at this side. P1 equal to, we know that P1 equal to this is the intensity of pressure at this point. So what is the pressure force is there? So force equal to P1, impact of pressure intensity into area. Similarly here also, and this is the frictional force. Now you just identify what is the let resolve the forces in the horizontal direction or in the fluid flow direction. So this is the This is positive because of the forward direction. This is negative due to reverse direction. This is also negative due to reverse direction. And just you solve it equation. Finally, you will get this is the HF equal to 4LV square by 2GT. I hope you understand this concept. Still, if you are having doubt, you can give a comment on the comment box. Thank you.